If you finished, just raise your hands. Done, right? Okay. Now listen to the story. Now, when you are talking about deformation, there are two types of deformation. One is permanent deformation. If not, we are calling it as plastic deformation. Deformations, there are two types of deformation. Deformation. One is permanent deformation. Permanent. If not plastic. Plastic deformation. Other one is non-permanent. That means elastic. Plastic deformation. Other one is elastic deformation. It just give the idea. What is the difference between plastic deformation and elastic deformation? I think you already know the idea. Permanent deformation means plastic deformation means when you provide the external force and when you deform the object, even though the external force becomes zero, even though you stop giving the external force also, object doesn't come back to the initial shape. Object stay at default condition, right? Yeah, when you provide external force, yes, object undergoes deformation. Even though you release the force, your external force is also zero also, object still at the deformed condition. That means object will never return back to its original shape. So that is we call as permanent deformation, if not plastic deformation. Then what's elastic deformation? Elastic means, yes, when you apply the force, yes, object undergoes deformation. Once you stop giving the force, object comes back to the natural size and shape. This is what we call as elastic deformation, like a rubber band. When you stretch it, it changes its shape and size. Once you remove the force, that rubber band will come back to its natural size and shape. That is the idea, right? Now we'll try to understand. Now you are going to apply the external force, and you are going to increase your external force from 0 to 1, 2, 3, 4, likewise. Then by increasing external force, you are going to change, you are going to increase your stress. You are going to increase your stress acting on the rod. Based on that, let's try to understand what will happen for the strain and what are the important points to be noticed. What are the physical changes happening in the rod? We'll try to understand by following a good story. Okay, first story. Right. Now, in the very first beginning, initially, what is the extension in the beginning? Initially, rod is under its natural length. That means no extension, no extension, no extension, and no external force. No external force. That means no extension. Then stress is also zero. Stress is also zero. Strain also zero. So then initially, graph starts from origin. That story very clear. Now, in the first few forces, in the beginning, we noticed that the stress and strain obtain kind of direct proportionality. That means when you are increasing the force remember, in the beginning, remember, right? In the beginning, you see that you are now the what is the variable that you are changing? You are changing the external force. So when you are increasing your external force in the beginning, accordingly, extension also changes. That means there is a kind of direct relationship between extension and the external force that you apply. There's a kind of direct relationship. When external force that you applied increases, accordingly, a change in length, if not extension, increases. based on this proportionality, we can write the stress strain proportionality. When you increase the external force, we know that automatically stress also increases. We know that stress also increases. Parallelly, when the extension increases, strain also increases. Since we know that L and capital A are constants, again there is a kind of direct relationship between stress and strain. You all know that when there is a direct relationship between stress and strain, you know in the beginning, how would be your graph? The graph should be a linear graph. In the beginning, the graph should be a linear graph. The graph should be a linear graph, right? The graph should be a linear graph. The beginning, right? Okay. This linear relationship, this direct relationship, direct proportionality between stress and strain exists up to a certain stress value only. Okay. Now you can now you are applying different stress values. For an example, 1, 2, 3, 4, 5. Likewise, up to a certain stress value, you notice kind of direct relationship between stress and strain. Okay, right. That that maximum stress, right? The maximum stress, we are calling it as proportional limit. That maximum stress, we are calling it as proportional limit. Proportional limit. Proportional limit. Right? I will tell you the story. Okay, I will explain. Don't worry. The stress is proportional to, if the stress, the strain varies with the stress in linearly until your applied stress is less than a certain stress value. That the maximum stress that you can apply in order to maintain stress and strain direct relationship, the maximum stress, we are calling it as proportional limit. Proportional limit, right? Now, first of all, we'll talk about, let's say now someone is applying a stress. Applying a stress means, stress means FOV. If I tell you that someone is applying a stress, you think that someone is applying a force, FOV. Force over area is stress. If I say someone is applying a stress means someone is applying a force. When you apply force on linear, you can apply stress. So hereafter, just keep in your mind, if I say when you are increasing the stress means you are increasing the force applied on that constant cross sectional area. Thing like that. Thing like that. Okay. Let's say there is a rod. Let's say a guy applied a stress, a value somewhere here. Then we know that this value is less than the proportional limit, right? So you apply the stress on the rod. That value, let's say that value is around 10 something. So this value that you applied is less than the proportional limit. Then what will happen? What will happen once you release the stress acting on the object? Once you release the stress, remember that rod will come back to the original length. That rod will come back to the original length. Okay. So when you apply stress 10 newtons per meter squared, corresponding strain is this is the corresponding strain. If you are reducing the stress again, remember corresponding strain also decreases. Finally, that object, that rod comes back to the original shape. Okay, when you apply a stress less than the proportional limit. And remember, the most important thing is if the stress is less than the proportional limit, the most important thing is if the applied stress is less than the proportional limit, we notice that there is a direct relationship between stress and strain. There's a direct relationship between stress and strain. This story we noticed. Right. For an example, for our understanding, let's say proportional limit is 20 something. Proportional limit is 20. This point I mark it as point capital A. Now, so then what will happen? So what will happen then if someone applies a stress greater than proportional limit? So then we notice that if the stress is just above, if the applied stress is just above the proportional limit, then also up to a certain stress value, you notice that when stress increases, corresponding strain also increases. If your applied stress is just above the proportional limit, then if the stress is reaches a certain maximum stress value, you notice again stress is varying with strain is varying with stress, but this time not linearly. When the stress was in between, when the stress was in between zero and proportional limit, yes, stress and strain had a direct relationship between them. If the applied stress is greater than the proportional limit, up to a certain stress, again stress and strain increases, but there isn't any direct relationship between stress and strain. Okay, the story. So then you notice that. So when you increase the stress further, now proportional limit is 20 newtons per meter squared. Now you are applying a stress greater than 20 newtons per meter squared. 21, 22, 23 newtons per meter squared. You are increasing your stress. Then you notice that as you increase your stress, you notice that your corresponding strain also increases. This time not in a linear manner. And reaches a point to call point capital B. Reaches a point called point capital B. Normally, this point capital B we name as proportional limit. This point capital we name as proportional limit. Okay. Capital A is we commonly call as point capital B is elastic limit. Point capital A is we call as proportional limit. Point capital we name as elastic limit. Elastic limit. This point capital B we call as elastic limit. Right? That is elastic limit. EL. EL. Right. EL. I will ask you a question. So then the idea is very clear. So we are increasing the stress. Then we notice that when the stress is less than the proportional limit, we noticed there is a direct relationship between stress and strain. When stress increases, corresponding strain also increased in a linear manner. Right? When the applied stress is just above the proportional limit, when the applied stress is just above the proportional limit and just below the elastic limit, if let's say that you are increasing the stress in between proportional limit and elastic limit, then also you notice that when you increase your stress, you notice corresponding strain also increases. But this time, there isn't any linear relationship between stress and strain. Yeah, when you increase your stress, your strain increases, but this time not in a linear manner. And the reaches point capital B. Okay. Now we define this point capital B as elastic limit. What is the meaning, sir? Why we define point capital B as elastic limit? Now you guys understood why we define point capital as elastic limit. Sorry, why we define point capital as A as proportional limit. Now you guys are very clear. You guys are very clear why we are naming point capital A as proportional limit, because we know beyond point capital A there won't be any proportional relationship. There won't be any direct proportionality between stress and strain. That's why we name point capital A is the proportional limit. So why are we naming this point capital B as our elastic limit? The reason is very simple. The reason is very simple. Let's say if you have applied a stress beyond elastic limit, then that object loses its property called elasticity. We know that because of the property called elasticity only, that object deformed due to an external force. Once the external force is zero, that object reaches back to its original shape. What will happen if you apply stress beyond the elastic limit? Remember, that object loses its elasticity nature. Then do you think will the object return back to the original shape even you release the stress? For an example, let's say now proportional limit is 20. Elastic limit is 40. Now you are applying a stress 41. 41 is greater than the elastic limit. When you apply 41 and once you release the object, remember, object won't come back to its original shape. Do you understand? Object won't come back to its original length. Let's say original length is, for an example, let's say 20 centimeter. When you apply 41 stress, then the length of the rod is, let's say, 41 centimeters. And when you release that 41 stress, you might expect that object would come to a length initially in 20, but object won't come to 20. Sometimes object will come to a length 22, 23. Do you understand? So very clear. If someone is applying a stress beyond the elastic limit, that object undergoes kind of permanent deformation. That object undergoes kind of permanent deformation. Please tell me, up to now, everything is very clear, hands up. Whatever I explained, everything is very clear up now, hands up. Idea is very clear, hands up. Idea is very clear. Now, story is very simple. We are going to analyze variation of strain with the stress, right? Yeah, but x-axis is strain and y-axis is stress, but we are changing stress and accordingly we are understanding how strain varies. Then we notice that, right? Until proportional limit, stress and strain directly proportional. Between proportional limit and elastic limit also, stress and strain increases with the stress, but not in a linear manner. But not in a linear manner. So the point where, if not the maximum stress, where this proportional behavior exists, that stress we called as proportional limit. The maximum stress you can apply to maintain that object's elasticity nature. We call it as elastic limit. Up to this very clearly. So what you draw, you should draw from here to here. Again, I will draw something in between also. Keep enough space. Once you finish drawing up to here, then we write the note. Once you finish the answer. So you don't write PL, write it as proportional limit. Proportional limit. EL means elastic limit. EL means elastic limit. Once you finish writing, just raise your hands. Once you finish writing, raise your hands. Right. Done? Okay. Then parallel discussing the writing the notes, we'll discuss one by one year after every point. Right. So then, so anyways, just mark this point capital A, point capital A. Now, yeah, this is proportional limit. Separately write down point capital A means proportional limit. And separately write down point capital B means elastic limit. In exams, essay questions, they tested this many times. Okay. So then, other than that, you can write down everything I explained here. And you don't need to write only my note. So when I explain, if you feel that something is important, then you can write as your own note. Okay. Then write down like this. Write down. Write down like this. The variation of stress strain graph. The variation of stress strain graph consists of consists of consists of straight line portion inside the bracket or capital A close the bracket. Consists of straight line portion inside the bracket or capital A close the bracket and curved portion inside the bracket write down A, B, C, D, E, capital A, sorry, yeah, capital A, capital B, capital C, capital D, capital E, close the bracket, right? Just now I explained up to O to A graph and A to B graph. I want to teach you about B to C, C to D, D to E story. I want to explain little by little, right? So once you finish doing the graph, the stress strain graph, you understand. So we can categorize the graph into two different portions. O to A section is a straight line variation. A to E is a kind of curvy nature, right? So we'll analyze, we'll understand why it becomes curvy and the reasons behind that. Everything we'll learn nicely. Okay, right. Then write down proportional limit capital E. Proportional limit capital A. Write down kind of topic something. It can be a topic or proportional limit inside the bracket capital A. Close the bracket and put a hyphen and write down. It's up to you. Write down. Write down. The strain varies proportionally. If you write like this, write like this. There is a direct relationship between. Right. Wait. Write like this. Write like this. Write like this. Write like this. I will tell you. The strain is directly proportional to the strain is directly proportional to the strain is directly proportional to the applied stress. Applied stress in the graph O capital E. In the graph O capital E. In the graph O capital E. Next point, write down under that topic, under proportional limit. You wrote first point. The second point, write down. Second point. The point at which this feature ends. The point at which this feature ends. Inside the bracket, direct proportional relationship, close the bracket. The point at which this feature ends, inside the bracket, direct proportionality. Direct proportionality, close the bracket. The point at which this feature ends, inside the bracket, direct proportionality, close the bracket, is called proportional limit. Is called proportional limit. Is called proportional limit. Now, just now I'm telling that point capital A is now here I'm defining that proportional limit is a kind of point, but that's wrong. Remember, proportional limit is it basically represents a stress. Do you understand? So the right idea is that stress corresponding to, if for the maximum stress you can apply to an object without impacting the direct relationship. If for the maximum stress that you can apply to the object, where stress is going to be directly proportional with the strain, is proportional limit. Inside the bracket, red color pen write down. Inside the bracket, red color pen write down. The stress corresponding to point capital A. The stress corresponding to point capital A is defined as proportional limit. Highlight stress proportional limit. The stress corresponding to point capital A is defined as proportional limit. Highlight that stress. That story is done. That story is done. Now, in mechanics also, we talked about this equation. In mechanics, you can remember, especially we talked this for springs. We know that in mechanics we learned mechanics. You can remember the story. So then, natural length of the spring is simple L, and when the force is, let's say, capital F, when the force is capital F, the corresponding extension we marked in simple X. So then we applied, we considered, we wrote an equation, F equals Kx equation. Right, so what is here F? F means we know that applied force. What is X? X means the change in length, if not extension. What is K? We define K as a force constant. Now only we are going to learn how this equation came. What the reason behind this stories. Now only we are learning properly. So you notice that. You notice when you are changing your stress, right? In the beginning, what happened? When you are changing the force in the beginning, within the proportional limit region, when you are increasing the force, you notice that your strain is directly proportional. That's why from this from this relationship only we derive then stress is proportional to strain. Do you understand? So write down a topic under that point. Huh? Now we are talking about proportional limit. We wrote some points. Then put your topic. Put your topic Hooke's law. Hooke's law. It's double O K E S. Hooke's law. Hooke's law. A topic. Hooke's law. Hooke's law. Now Hooke said that if the applied stress is less than the proportional limit, if the stress that you applied is less than the proportional limit, then Hooke said that stress is, then Hooke said that applied external force is directly proportional to the, if not elastic force. I told you elastic applied external force is the elastic force. Hooke said that elastic force is directly proportional to the change in length. Elastic force is directly proportional to the change in length. That can be extension or compression. That can be change in length means increase in length or decrease in length. To remove the proportionality, we are using constant. That constant we call as what? Force constant. That constant we are using as force constant. Right? F equals Ke. Now in here we define K as spring constant. Now here this K means force constant simply. These two equations are very similar, same equation. Same equation. Okay. So then K means, remember, K means force constant. Then you know what is E, we define E, you know what is F. K means force constant. Force constant. Right? Remember, in the essay questions, they can make you what? Very tricky. They can ask a very tricky question. So they can make you confused that. Remember, sometimes they ask you to apply this Hooke's law. If not this F equals K equation, somewhere in between A and B. Sometimes they might manipulate you to apply this F equals K equation somewhere in between B and C, C and D. Remember, we can apply F equals K equation only in this region O to A. Okay, we can apply Hooke's law when the stress varies linear with the strain. We can apply Hooke's law when the applied force, external force, varies linear with the extension. Right? If not, if you apply stress is less than the proportional limit only, you can apply Hooke's law. Do you understand? Right? So now you put the topic Hooke's law and different color pen write down. Put your topic Hooke's law and different color pen write down. Different color pen write down. Put your topic Hooke's law and different color pen write down. Write down. Within the proportional limit, comma. Within the proportional limit, comma. Even use red color and fine. Within the proportional limit, comma. The elastic force is directly proportional to the extension. Within the proportional limit, comma, the elastic force is directly proportional to the elastic force is directly proportional to the extension. So write down this uh, when the applied stress is less than the proportional limit, right? This is the main proportionality. Yeah? If proportional to the extension, so this is not only for extension. If it can be a compression also. When the length increases, that change in length we name as extension. When the rod compresses, if you apply a force like this, length going to be reduced. Then simply going to be our compression. Now I define for the extension, right? Write down K. Submit K and find the dimensions of K. Find the dimensions and units of K quickly. Quickly find the dimensions and units of K. So if we substitute K, then we know that Q means what? K means F over V. K means we notice that F over V. K means we notice that F over V. K means F over V. Then the units of F means newtons. The units of extension going to be meters. Then the units of force constant. Remember, Newton, this is meter, Newton per meter. Newton per meter. Right. So next point, write down, after writing this equation, write down the units of force constant. Newton per meter. And write down the dimensions of force constant also. Write down the dimensions of force constant. The dimensions of force constant. Dimensions of force constant. Write down dimensions of force over dimensions of extension. Force dimension is going to be M LT minus 2. Extension dimension is going to be capital L. Then we can write down dimensions of force constant is mt to the power minus 2. Nice story. Nice story. Finish it. Finish it. Right. So then I think I explained all the important points to be remembered regarding O to A region, linear graph region, linear. Now we'll talk about then proportional limit we discussed. Then we'll talk about that elastic limit. Right. Before putting the topic elastic limit, write red color pen important. Red color pen important. Write down. Hooke's law should only be applied. Hooke's law should only be applied. Important. Red color pen. Hooke's law should only be applied within the proportional limit. Within the proportional limit. Again and again, I'm telling for a reason. Within the proportional limit. Next point also write down. The next point, blue color pen is okay. If the applied stress is below the proportional limit, if the applied stress is below the proportional limit, I told you, so when you apply a stress below the proportional limit and when you release the stress, what will happen for the object? Object will come back to its natural length, right? So we will write it as a point also. If the applied stress is below the proportional limit, then the rod will, if not then the wire, this can be a wire or string, then the object will come back to its original length. Then the object will come back to its original length. Then the object will come back to its original length once the applied stress is removed. 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 So this is the only complex thing. Thereafter, very simple stories. We'll talk about that. There are two equations. Then tomorrow we'll do past papers. Next day also we'll do tute questions. Likewise, we'll finish it. Okay, don't worry. Right? Okay. So now put your topic that elastic limit. Elastic limit. Next topic. Inside the bracket, point capital B. Close the bracket. Close the bracket. Now I explain. So what will happen? If your applied stress is greater than proportional limit and below the elastic limit, if your stress varies between proportional limit to elastic limit, we notice that even though strain increases with the stress, there isn't any direct relationship between stress and strain. Yeah, obviously, when the stress increases from proportional limit to elastic limit, yeah, strain increases, but there is any direct relationship. They are not linear. Write down next point. Elastic limit instead of that point capital B, write down under that, write down under that, write down. Although strain increases with stress, although strain increases with stress from capital A to capital B, from capital A to capital B, Inside the bracket, you can write down elastic limit to proportional limit. EL to, sorry, PL to EL. Inside the bracket, you can write down PL to EL, close the bracket. Although stress increases with stress from A to B, inside the bracket, PL to EL, close the bracket. But strain is not directly proportional to the, but stress is not directly proportional to the strain. But stress is not directly proportional to the strain. But stress is not directly proportional to the strain. Right? Then we know that if the stress is not proportional to the strain, look here, we know that if the stress is not directly proportional to the strain, then can we apply Hooke's law? Hooke's law says that force is proportional to the extension. If the stress is not proportional to the strain, we know that force is also not going to be proportional with the extension. Therefore, remember, we can't apply Hooke's law. Red color pen write down, red color pen next point. Next point, red color pen write down. Therefore, Hooke's law cannot be applied between A to B. Therefore, Hooke's law cannot be applied between A to B. Inside the bracket, above PL, above proportional limit, close the bracket. Above PL, close the bracket. That's also discussed. Done? Done. Next point, write down. Next point. If you can understand this graph, that's it. This lesson finished. So we'll practice more questions, then you will be very familiar. Right? Next point, write down. However, next point. However, in the region from O to B. However, in the region from O to B. However, in the region from O to B. In the curve, comma, when the stress gradually decreases, when the stress gradually decreases, when stress gradually decreases, the strain also gradually decreases along the curve itself. The strain also gradually decreases. The strain also gradually decreases. The strain also gradually decreases along the curve itself. Along the curve itself. Now I told you. So then when you consider, so when you are applied stresses in between O to B, if you apply stresses in between 0 to elastic limit, we know that our object is having elastic nature. If you apply a stress that is less than the elastic limit, then we know that that object has that elasticity property. Then we know if that object has elasticity property, when the stress is reduced, strain also reduces, and finally object will come back to its natural size and shape. So that's what they are telling. When we consider O to B section, if you are reducing the stress, then we know strain also decreases. And then you can consider along the graph, when you decrease the stress, along the graph, strain also decreases. That is what they are telling in that point. Right? So red color right. Next point, write down. Next point. Next point, write down. Write down. So when the stress is completely removed, when the stress is completely removed, when the stress is completely removed, the wire, in front of the rod, whatever, the rod in front of the object, the rod attains its exact original length. The rod obtains its exact original length. The rod obtains its exact original length. Okay? Full stop. Okay, right. Different color pen write down. If for red color pen also you can use. Elastic limit is defined as the elastic limit is defined as the elastic limit is defined as the maximum stress, maximum stress, maximum stress, maximum stress that a material can withstand. The maximum stress that a material can withstand before the permanent deformation. Before the permanent deformation. Before the permanent deformation. I will ask a question. You just raise your hands, okay? Raise your hands. How about we say? Now there is an object. That object's elastic limit is given as 40 pascals. That object's elastic limit is given as 40 pascals. Raise your hands. How about we say? When we apply 39 pascals, then that object will undergo permanent deformation and if I apply 39 pascals, now elastic limit is 40 pascals. If I apply 39 pascals, raise your hands, how many we say that object will undergo permanent deformation and that object will undergo elastic deformation and that's story clear. Next point, if you're applying a stress, let's say 45 pascal, its elastic limit is 40, you apply 45 pascals. Raise your hands, that object will never return back to its original length and if you apply 45 pascals, that object will never return back to its original shape and never returns. Because why? Because the elastic limit is 40, but if you are applying a stress 45, that is greater than the elastic limit. If you are applying a stress greater than elastic limit means it undergoes kind of permanent deformation. So therefore, that object won't return back to its original length. Its length might reduce, but not exactly to its original length. Do you understand what I'm saying? That is the idea you want to understand there. I think this part is very clear. This is the part that we want also. This story is very clear. I explained everything properly. Everything properly. Now, when you apply for, now, if someone asking a question, sir, right, when we apply stress less than elastic limit, yes, obviously, object will undergo elastic deformation. If we apply a stress greater than the elastic limit, it undergoes permanent deformation. So what if we apply stress exactly equal to the elastic limit? So then since it's not exceeding, so when you apply stress equal to the elastic limit, then we can consider then also object undergoes elastic deformation. Then also object undergoes elastic deformation. That story is clear. That story is clear. Thereafter story. Okay. Right. Okay. Everything is explained properly. Right. Better exponents write down. Exponents write down. Uh, in the region OB, in the region AB, sorry, in the region AB, in the region AB. Oh, in the region OB, in the region OB, in the region OB, the rod, if not the wire, undergoes elastic deformation. The rod or the wire undergoes elastic deformation. Done. Up to now, everything is crystal clear and up to now, everything is very clear and all the ideas, everything is very clear and so if you have any doubts, you can ask your doubts also. Right. That story is done. So once again, just raise your hands. Everything is very clear and if you have any doubts, please ask. If everything is very clear, just raise your hands. Right. Okay. Done. That story also done. Right. Now put to our next topic. Next point. Now we discussed about proportional limit. Then we talked about elastic limit. We'll talk about what is this yield point. Next one, yield point. Next one, yield point. Right. Okay. So now what happens? Sir, if I apply stress beyond elastic limit, what will happen, sir? Then if the stress is beyond elastic limit and if I'm increasing the stress. So won't that wire rod undergoes strain? Won't the length of the rod increases? Yes, increases. Yes, increases. Is the story? The story. Now you are applying a stress beyond the elastic limit, and when you increase the stress, remember, then what happens? Then what happens? Actually, that rod now beyond point capital B, right? When you consider the nature of the rod, that rod has elastic property as well as slightly that object that rod has elastic property as well as it has kind of plastic properties, right? When you consider when you apply stress beyond the elastic limit, that rod has some kind of elastic property as well as. Give me a second. Give me a second. Right. So when you're exceeding beyond the elastic limit, that rod has elastic property as well as plastic property, slightly elastic property, but mainly plastic property. Now what happens when you apply more and more and more force, and when you are increasing your stress more and more, then what happens? The medium particles try to skid on top of each other, right? For an example, see this. Uh, Give me a second. Give me a second. Uh, Need a break, hands up. Hands up, need a break, hands up. Need a break, hands up. So we'll take a small break. Come, now time is 9:27. Come at 9:45. Take a small break and come. We take a small break and come. Come at 9:40. Take a break. ආශා මේ අරකේ මේ දැන් ඒ තැන්වල මම ඇවිල්ලා මේ question numbers දාලා තියෙනවානේ. ඒ කියන්නේ දැන් note එකේ blank තියෙනවා. ළඟට මම question numbers දාලා තියෙනවානේ. ඒතකොට ඒ දාලා තියෙන question numbers ටික ඒ තැන්වලට දාන්න ඕනේ ආශා. තේරෙනවද? අෂන් මේ අර ඔය අන්තිමට තියෙන ටික ඇවිල්ලා දැන් අපි කලින් ඇවිල්ලා ඒ තැන් වලටම ප්‍රශ්න අංක දාලා ඇතිනේ අර ටියුට් එකේ ඒ අර ඒ කියන්නේ නෝට් එක හදාන් යද්දී තනින් තන දාලා තියෙන ප්‍රශ්න නම්බර්ස් ටික ඒ ප්‍රශ්න ටික ඒ තැනට එන්න ඕනේ මේ දැන් ආයේ ෆොටෝ එකේ තියෙන ප්‍රශ්න ටික අන්තිමට ඇවිල්ලා මොකද කරන්නේ අන්තිමට දාන මාතෘකා ටිකක් දානවා දාලා තියෙන්නේ මේ lateral displacement කියලා මේ ඒ අර්ථ මේ ප්‍රශ්න ටික easy difficult moderate වගේ ඊළඟට ඒ අන්තිමට ඔය වෙනම ටොපික් ටික දාලා ප්‍රශ්න ටික දාන්න තියෙනවා. Yes. Right. Okay. So then we discussed O to B. We talked about proportional limit. Then we talked about elastic limit. Now we'll try to understand what will happen when you apply stress beyond the elastic limit. Okay. So write like this. Write like this. Beyond the elastic limit, capital B, comma, exceeds the yield point. Exceeds the yield point. Exceeds the yield point. YIELD. Yield point. Full stop. Between these 2 points, between these 2 points, comma, between these 2 points, that means elastic limit and yield point. Between these 2 points, comma, the extension occurs, the extension occurs, the extension occurs according to the force applied, according to the force applied, according to the force applied, due to the elastic property in the wire as well as, due to the elastic property in the wire as well as, due to the elastic property in the wire as well as, due to its plastic property, due to its plastic property. Okay, due to its plastic property. Full stop. I explained already. From O to elastic limit, that object, that wire only has elastic property. From O to elastic limit, remember that object does not have any plastic property. But when the stress is beyond elastic limit, remember elastic limit to that yield point, that wire having both the properties, small amount of elastic property and increasing plastic property. So therefore, when you apply stress beyond the elastic limit also, when you apply stress beyond the last limit also, wire undergoes extension. But the problem is, we might notice the medium particles in the wire sit on top of each other. There's a kind of slip of the medium particles on top of each other, right? That means some kind of, that means what's happening internally, medium particle dislocate. So when you keep on increasing the stress beyond the elastic limit, that's why medium particles slip on top of each other, right? Between point capital B and point capital C. Okay. So we wrote what we wrote, elastic property in the wire as well as due to its plastic property. Full stop. Next point, write down this plastic property. This plastic property is a result of. This plastic property is a result of sliding of the internal molecules. This plastic property is a result of the sliding of the internal molecules. Is a result of the sliding of the internal molecules, internal molecule layers, internal molecule layers of the wire between each other, of the wire between each other, of the wire between each other, of the wire between each other. Right? I told you. So then when you consider, if I do that part in the graph, if I do that part in the graph, they ask everything. Just when you do essay questions, planning to do an essay session also in this week, then you will understand. Right. Okay. Okay. Then B to C. The B to C. that part, if I draw that part, so you guys careful to the graph, huh? If I draw B to C that part, this is your C, yield point. This is your C, point C, yield point. So the stress corresponding to the yield point. The stress corresponding to the yield point is the stress corresponding to the yield point, right? This C is the yield point. Now just mark A is proportional limit, B is elastic limit, C is yield point. Write down. Okay, done. Now I will ask you a question. So when your stress is in between elastic limit and yield point, let's say somewhere here, once you release the stress, raise your hand, somebody will say that this Y will come back to its original length and Y will undergo permanent deformation and it will undergo permanent deformation. Do you understand? Right? If you apply stress in between elastic limit and yield point, since it undergoes, because why? Because it undergoes plastic deformation. That's why medium particles slide on top of each other. So then there is a permanent deformation. But some people think like this. Okay, some people have misunderstanding like this also. Sir, now according to what you are explaining, sir, when someone applies a stress in between elastic limit and yield point, and when the stress is released, sir, let's say now this is the natural length of the rod. Now I'm applying a stress between elastic limit and yield point. Then the rod is uh, extending to a length like this. Some people think that once the stress is released, some people think that that rod won't decrease its length. No, it reduces its length, but it's not fully reaching the natural length. Right? When you release the stress, the length of the rod decreases and try to come to the original length, but it won't able to come to the original length. Still, its length is greater than the original length. That's why we're telling there's a kind of permanent deformation there. Do you understand? Somehow, initially, when you release the stress, there's a reduction in the length of the rod and it tries to come back to the original length. But unfortunately, it stops in between. It can't exactly reach its earlier original length. That is the idea. Okay, that is the idea. Right. Okay. So then I was explaining what? I was explaining this plastic property is a result of the sliding of internal molecule layers of the wire between each other. Right. Okay. Okay. So you put that under the topic yield point only you are writing, right? Under the topic yield point only you are writing. Then write down. Then write down next story. It's a big graph story. Okay. Right. So what will happen? Okay. So then okay. Then between B to C, that object has slightly elastic properties as well as increasing plastic properties. So between C also remember, object is only having plastic properties. So when you further increase your stress beyond the yield point, for a small increase in stress, there will be a large increase in strain, right? If your stress is beyond the yield point, even you increase your stress by a small amount, even increase your stress by a small amount, remember, your strain will be increased. Your strain will be increased by a large amount. Why? Now it fully undergoes plastic deformation. That means molecule particles are sliding larger manner. That's a result, a large increase in strain. So if I draw that part, if I draw that part, draw the graph. If I draw that part, then that part, draw the graph properly. Then you will see, right? Then you will see, right? This is point capital D, point capital E. So mark this, mark this. So the C is the yield point, right? Okay, right. Okay, write down, write down. Uh, Next point, beyond the yield point, comma, the extension in the wire. Beyond the yield point, comma, the extension in the wire is mainly due to, is mainly due to its plastic property, is mainly due to its plastic property, is mainly due to its plastic property. Full stop. Red color pen, red color pen. Thus, in this portion of the graph, thus, in this portion in the graph, thus, in this portion in the graph, a low increase in tension, a low increase in tension, a low increase in tension shows a, shows a, shows a large increase in extension, shows a large increase in extension, shows a large increase in extension. That means low increase in stress results a large increase in strain. That's the idea. That's it. Okay, right. So then, okay. So then, what will happen thereafter? Now, when you are applying the stress more than the yield point, then we know continuously wire undergoes plastic deformation. That means medium particles slides on top of each other, and right. As a result, even you increase your stress little by little bit, your strain increases drastically. Then you notice that. Then you notice that. As a result, you notice, right? As a result, you notice that there is a kind of reduction in the cross section area of the rod, right? So, what is capital D? Capital D we can tell as capital D we can name it as breaking stress. Okay, capital D means breaking stress. Why? Sorry, capital breaking stress. The maximum stress that rod can withstand. Now you are keep on increasing your stress. You are applying a more and more large stress on the rod. The maximum stress that the rod can withstand before the rupture, before the breaking, is we call as the what? Maximum stress, we call it as breaking stress. Okay, what will happen if you try to beyond this breaking stress, if you try to increase the stress by 1 or 0.001, what will happens? You notice a sudden reduction in the cross section area of the rod. You notice when you try to apply stress beyond that breaking stress, you notice a sudden reduction in the cross section area of the rod, a sudden reduction in the cross section area of the rod, a sudden reduction in the cross section area of the rod. Then at a point in between, at a point in the rod, at a point in the rod, at a point in the wire, at a point in the wire, cross section area suddenly decrease, and at a point it starts breaking. Starts breaking. Right? Is the idea. Is the idea. So write down point capital D as write down. Point capital D means write down. Point capital D means write down. Uh, Point capital D means write down. Mm, right. Point capital D means breaking stress, and point capital E as rupture point, if not breaking point. Breaking stress. This is breaking point. Breaking stress, rupture point, if not breaking point. That's the idea. Hands up. This graph and this idea is everything is crystal clear. Hands up. This idea is very clear. If you understood what I explained here, everything is very clear. Hands up. Everything is very clear. Hands up. Clear? Nahi? Right. Okay. Clear. So we'll write the last point. Last point we'll write down. We'll write down. Write down. Write down. Okay. Write like this. The maximum stress. The maximum stress that the wire can withstand before breaking is breaking stress. The maximum stress that the wire can withstand before breaking is breaking stress. Okay, continue. Next point. After point capital D, after point capital D, the wire gets thinner and the wire gets thinner and after point capital D, the wire gets thinner and 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 breaks at a point capital D, breaks at a point capital D, which is called as breaking point if a rupture point. Okay, done. That's story done. So that is the difficult part in the lesson. But I think that after understand this idea, they are after very easy. Remaining stories are very simple stories. Okay. So everything is very clear and crystal clear. Genuinely, this idea. This is the only difficult idea. Other than that, we have to do right. We have to learn 2 or 3 equations, and that's it. We don't have any theory that much. This story genuinely, did you understand? If you have doubts, you can ask. This story is very clear and seriously very clear. This story is very clear. Right. Okay. So then, what shall we do now? Right. So now put a topic that now topic. Write down now topic. Young's modulus slash elastic module. Young's modulus slash elastic module. Young's modulus slash elastic module. Right. Young's modulus slash elastic module. Young's modulus. So if not, we call it as elastic module also. Elastic. Now there is a rod. Its natural length is simple L. Then if the rod is under its natural length, initial applied external force is 0. You want to assume the cross-sectional area remains constant even we apply the external force, even the rod undergoes extension. So initial external force applied to the rod is 0. Natural length is simple length. So when you apply the external force and when the rod undergoes extension, more the rod extends, the required external force also increases. Okay, so you have that experience when you are when you are stretching the rubber band also. You notice when the rubber band stretches more and more and more and more and more, the required force you want to provide the rubber band to stretch also increases. The same manner, right? Let's say at a certain instant, the extension and corresponding external force acting on the rods are, let's say, simple E and simple F, simple E and capital F. The external force acting on the rod is capital F. Extension, corresponding extension, simple E. Okay. Uh, Already, if you assume the stress, now you want to consider cross-sectional area remains constant. Then let's say the stress acting on the rod at this instant is below the proportional limit. What is stress? If I say the cross-sectional area is capital E, cross-sectional area of the rod, let's say capital E, then when the external force applied is capital F, corresponding stress will be F over A. F over A. If that stress is less than the proportional limit, we know that F is directly proportional to the extension. Am I correct? We can write down F is proportional to the extension. Because why? It obeys Hooke's law. Then what can I do? I can divide both sides by uh, capital A and simple A. I tell you the reason. Here F and E both are variable, right? So when you are increasing F is a variable. Based on that, simple E also increases is a variable. So when you divide a variable by a constant, there isn't any overall impact for the direct proportionality. When you divide a variable by a constant, natural length, there won't be a overall impact to the proportionality, right? So therefore, we can write down F of A means stress, stress proportional to the strain. To remove this proportionality, we are using constant. The constant is, we are calling it as the modulus, Young's modulus. If not, we call it as elastic modulus. Some people use capital Y, some people use capital E. I also use capital E here, but in some questions they are using elastic modulus, Young's modulus as what? Capital Y also, right? So capital E, epsilon, right? This is the equation. Remember, they can ask you a question: what is the relationship between stress and strain? Stress equals Young's modulus, elastic modulus in the strain. It's one equation. Okay, right. Then shall we substitute elastic modulus? We substitute elastic modulus, that is equal to stress over strain. Stress over strain. Stress. What is the units that we use to measure the stress? Stress is, we know, you want to understand, it's some kind of pressure. Stress is kind of a pressure. Therefore, newtons per meter squared, if not pascals. The strain does not have any units or dimensions. No units. Therefore, remember the units of Young's modulus, elastic modulus also, newtons per meter squared. Basically, this constant depends on the material property. So, different materials have different Young's modulus or different elastic modulus. Keep in your mind, right? Okay. So, write down this story. Once you finish drawing, raise your hands. Once you finish drawing, raise your hands. Once you finished, raise your hands. If you finished, answer. Okay, done. Done. So that part is also done. Write down. Find the units of elastic modulus newtons per meter square. Next point is dimensions of elastic modulus. Also, I taught you. Find the dimensions also. ml minus one, t minus two. Because you know the dimensions of stress is ml minus one, t minus two. Then dimensions of elastic modulus also ml minus one, t minus two. Write down the units of elastic modulus is newtons per meter square or pascals. Dimensions of elastic modulus is ml minus 1 t minus 2. Dimensions of elastic modulus, Young's modulus is ml minus 1 t minus 2. Write down, write down, write down. And mention this as elastic modulus. Elastic modulus. Right. Okay. Or point write down. Elastic module is a proportionality constant. Elastic module. Elastic module, if not modulus, is a proportionality constant. Is a proportionality constant. Which depends on the material. Which depends on the material. Right. Okay. 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 Right. That's okay. Right. Now, elastic and Young's models, both the ideas are pretty much similar idea. Okay. Same story only. But normally we specify Young's models as if the stress is below the proportional limit. If the stress is below the proportional limit, we say that we say that uh, the proportion, the ratio of stress to strain as Young's modulus, same idea only. Therefore, I'm not going to give that note, no need. So now, okay, then remember, then you have learned F equals KE equation under Hooke's law, and stress means force over area equation. Strain means E over L, change in length over natural length story you learned. Relationship between stress and strain. Stress equals elastic modulus into strain, if not Young's modulus into strain. And the next equation is, remember now, F over A means E over L. So you can write down important, and you can write this equation also. Sigma means F over A. F over A equals Young's modulus E over L. If not Y, E over L. You can use any equation, right? Highlight this also, highlight. This equation also highlight, right? That's it. That's it. Right. So we can do questions. So we can do questions. Before doing question, I will teach you next story also. I will teach you next story also. Then tomorrow, possible discussion, we can do something. We can do some good MCQs also. Then you get the idea. Next story, write down the last theory section. So after this theory section, there is only one story. One story means what will happen when there's a change in temperature. If a rod cannot if a rod cannot stretch, now you are increasing the temperature, but the rod cannot stretch. In that case, what will happen? Story only there. Don't I will teach you. Write down the next story. Next topic. Write down. Next topic. Write down. Elastic potential energy slash strain energy. Elastic potential energy slash strain energy. Elastic potential energy slash strain energy. Right. Okay. Right. So there is a practical from this unit also. What we will do? Write down. Now same story. Okay. The idea. Okay. Right. Look here. In mechanics you guys derive the equation. What is uh, the equation you derived in mechanics and the equation you are going to derive now? Both are same equation, right? You can remember. You can remember what is the equation we learned to find the elastic potential energy. Elastic potential energy means we know that half k x k art. If not, there's another equation, half f x ne, half k x k art. If not, half fx, right? So that equation basically gives what? Elastic potential energy stores in a elastic object. That means when you are trying to stretch the object, the amount of energy that do, sorry, the work that we do on the object, storing as kind of energy, that is the elastic potential energy that we have discussed in lastly that discussed in mechanics. The same thing again we are learning in different perspectives, same story only. Now what's happening now? Okay, there is a rod that natural and simple. Then initially applied external force is zero, right? So then you are applying external force, and when the rod starts to stretch more and more and more and more, every instant, every instant when the rod stretches, it changes, then the corresponding force that you applied is also increases. Am I correct? Let's say now current extension is 5 centimeter for an example. When the extension is 5 centimeter, corresponding force, let's say 50 newtons. When the extension is 1 centimeter, corresponding force is 10 Newton. When the extension is 20 centimeter, corresponding force acting on the rod is 20. When the extension is 3 centimeter, corresponding force 30. Extension 4, corresponding force 40. When the extension is 5 only, corresponding force is 50. So we notice that during the extension from 0 to simply, the external force applied to the rod varies from 0 to capital F. That means we can understand the force that we applied to obtain simply extension is not a uniform force. The force you applied, the force you applied to obtain simply extension is not uniform from the beginning to end. Agree? Agree? More the extension happens, the required force also increases. So actually, you have applied a variable force from here to here. In mechanics, I taught you that when there is a variable force acting on object, if you want to find the work done by that force, I told you that you want to consider average force acted on the object throughout the time period as the force acted on the object. You understand? We're very clear here to here. The force acting on the rod is varying, increasing. If there is a variable force acting on the rod, if you want to obtain an average force, what do you do? So you want to add 0 plus F over 2, right? Okay. So what I'm doing right now, look what I'm doing. Okay. So again to the diagram, this diagram again. L0, here F, corresponding elastic force also reverse direction, backward direction F. Again, do this diagram again. This diagram again. This F, cross section area is capital A. This diagram. Draw it again. Draw it again. Draw it again. Now I just do the many classes this month as much as possible, and electric field also I want to do. Yesterday I wanted to do, actually yesterday I could not do. Today and tomorrow also might be Wednesday 6 1 or something I will do because I want to finish it. Parallelly, I'm doing past papers also. Now, many night sessions I like to do with you, but need your support. If not difficult, right? We'll see. 26 batch is won't I won't finish 26 batch this much a big stress. So as you know that it's a bit well planned batch. 25. I'm doing my best. You agree with that? I told you in the beginning what happened to 25 batch. Based on that only, there are some delays. If not, I am very committed to teaching also. 26, no issues at all, and there are many plans for them. For you also, in the last month from January onwards, the plans I build for you. The work I have done, sometimes you also never have imagined, right? Still, I am okay to do until October. Still, I am okay to do with your energy, right? I want to do, I will do, but I need your energy also. Need the support from your end also. So then we can do the stories nicely. Okay. 26, that's a big plan for them. 27 also, obviously, right? Okay. Anyhow, we have enough time. 4 months. We have 4 months. If I can finish this unit 10, definitely we want to finish this month. Unit 6, we want to finish this month. Definitely, some more putting extra class, 1 hour or half an hour or daily. Or however, we should do class and we want to finish. Then unit 7, and I plan to do unit 11 also. But I am giving much priority for electric field. Unit 11 and unit 7. Then we want to do in August. Then we only have electronics in September. So then we can do electronics part in September. So therefore, this month and next month I will do the classes as much as possible and I will cover it. Okay. And parallelly, I'm doing the past paper stories and all. Right. All my slots are occupied for your batch only. Right. So therefore, need your support. So then we can do all the discussions and we can nicely finish the class. We can nicely finish. In the beginning, there was an issue with the batch, but in the end, from the January onwards, I think that I have done for the batch that I never have done for my previous batches. People who came for 24 batch, they know that I haven't worked this much for 24 batch. 24 batch, mainly it was a physical class. I didn't do a big go. I didn't even do a nice online class. What I was doing in the physical class, I just lively streamed. That's what I have done there. But from January onwards, the thing that I have done, I never have done for any my previous batches, right? So therefore, your support and everything is important. Then only we can go on a nice path, right? If I see there are some students are eagerly working with me, then we can work. Right, do the questions, night sessions, night time beyond 10:30. You can stay morning, do reduce going schools and going physically classes also, I'm telling. Right, we have 4 months to go, and night times joining for class, especially my classes night times 10:30 to 12:31. That is your normally less effective time, the less effective time. If you are staying at your home, and if you work from early in the morning, normally night time means very sleepy, and even you sit and you study also sometimes, because since you are working from early in the morning, since you're working from early in the morning, then it's very less effective time. In the less effective time also, if you forcefully, if you can make yourself to join for the sessions, then I think even night time also you can spend effectively. That's why putting in the night time more classes, right? And okay, now from this week onwards, we'll do these final papers properly, right? I give my maximum to mark everything, and 15 papers will write properly. Uh, Full papers means that 50 MCQ first day, next day only we have to discuss for essay for structured, because we want to discuss also, we don't have time. That's a problem. So we can't put 2 days for. If I discuss a full paper 1 week, one full paper means discussion time is not possible. That's a problem. But if we can finish quickly theories, and we can do something. But this month I think better we do 50 MCQ first week, for structured for essay something in second week. Likewise we can do, and I'll mark and get the papers as much as possible in my end. Right, need your support. Okay, right, okay, okay, right, okay. So then finish drawing hands. Finish drawing hands story. Finished. Because I was expecting a good crowd at the night time, since we are working the last time. People, friends also, they like to work me. But I noticed kind of there are usually two the students. Whatever, even I put class early in the morning, also they come and they join. Sometimes I also get demotivated actually. That is just everyone not doing like that. Normally they do one theory class, one revision class means 3 or 4 paper class to 1.5 an hour to write the paper, and 2 hour discuss. No one is doing past paper discussions likewise. So then actually recently I got bit demotivated. That's what happened. Need your support. Okay, then we can do a nice class and we can finish our classes properly. Okay, right. Okay, done. Done. Right on. So you agreed me. You agreed that the elastic force. So the external. Now you agreed the external force acting on the rod varies in this time period. In that case, corresponding elastic force also varies in this time period. You know that always I told you that elastic force always going to be equal to the external force you applied. Right? When the external force varies from 0 to F, your corresponding elastic force also varies from 0 to F. Only difference is elastic force acting opposite to the external force. So write down a point. Average elastic force acting on the rod equal symbol. Average elastic force acting on the rod equal symbol. Average elastic force acting on the rod equal symbol. Write down 0 plus F over 2 ni. 0 plus F over 2. 0 plus F over 2. 0 plus F over T. Average elastic force. That means F over 2. Next line write down. Therefore, work done on the rod. Therefore, work done on the rod equal symbol. So, in mechanics, we learned work done means force in displacement. So, in the attempt of extending the rod with an extension simply, the work done on the rod, W equals what? W equals the force acting on the rod is the average force. That is how much F over 2. Displacement is what? That is the extension of the rod simply. So the work done acting on the rod is how much? Half Fp. Half Fp. So this is what we learned there as so we derived the elastic potential energy equation half k x squared also similar manner. First of all, we found the work done acting on the rod. Then we told that that is the work done storing as the energy inside the rod. That is the elastic potential energy, right? So write down W equals half Fp. The next point, a different carbon write down, different carbon. That is also kind of equation in different carbon write down. The elastic potential energy storing on the rod slash strain energy equal symbol. The elastic potential energy storing on the rod slash strain energy equal symbol. Work done on the rod. 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 Right? So then write down. Finally, the equation strain energy means elastic potential energy. If not strain energy means remember half Fe equation. Strain energy that is remember half Fe. Highlight half Fe highlight. Right. So there is another story. This is strain energy, right? Strain energy. They can ask another equation. Strain energy per unit volume. Remember the strain energy per unit volume means just consider the cross sectional area of the rod is capital A. Initial length of the rod is capital A. Then tell me what is the initial length of the rod? Initial length of the rod. So initial length is capital simple L. Cross sectional area is capital A. Then what is the initial volume of the rod? We know that initial volume of the rod is what? Capital A into simple A. Initial volume of the rod. So we all know that capital A into simple A. A strain energy equation, when you consider that entire rod, the elastic potential energy storing on that entire rod, we name as strain energy, that is half Fe. So what is the initial length of the rod? Simple L. What is the initial volume? A into L. So one can tell that for the initial volume AL, due to the extension, the stored elastic potential energy is the strain energy stored is half FV, half FV. For the initial volume A into L, the stored elastic potential energy is half FV. So for a unit volume, for a unit volume, the stored elastic potential energy for a unit volume, the strain energy, that is what? That is half FV over the volume, AL, right? So this is what we call as the, when you divide the strain energy over the volume, initial volume of the rod. This is we call as the strain energy per unit volume. Strain energy per unit volume. When you consider 1 meter cube initial volume, what is the elastic energy stored? For an example, 5 chocolates, 100 rupees. One chocolate, how much? 20 rupees. That is the idea. For the entire initial volume AL, the stored energy is how much? Half FE. For the 1 meter cube volume, how much is stored is what? You want to divide by the volume. So write down next story. Strain energy per unit volume equals, write down. Strain energy per unit volume equals total strain energy over total volume. Equation highlight. Strain energy per unit volume equals total strain energy over total volume. Highlight. Then write down strain energy per unit. Next line. Strain energy per unit volume equals half FE over AL. Half FE over AL. Somewhere else write down inside the bracket. Initial volume of the rod equals AL. 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 Done nih. Done nih. Correct nih. Correct. Okay nih. Right. So then you can write down. You can write down. See, half. Look here. Here you can write down. Strain energy per unit volume means half F over A E over L. F over A means we know that is the stress. Half stress. E over L means that is strain. Half sigma epsilon. Highlight this equation also. Half sigma epsilon highlight. Half sigma epsilon highlight. Equation. Equation. Right. That's it. That is theory wise. That is a theory wise story. Theory wise story. Cute questions we will do. Definitely we are doing. So there is one last theory part. There is one last theory part. Right. So we'll do the last theory part also. Next theory part. And also here the strain energy means we know. Okay. So if you know the variation of y-axis extension, your x-axis force. So the area under stress strain graph represents what? Strain energy. Okay, draw this graph also. On this graph. Right. Okay. So then we put the next topic, that topic story. Write down. There is a last theory part. Then elasticity theory wise everything is discussed. But what are the questions? Tomorrow I will do past paper MCQ tomorrow, and revision class plan I didn't mention because I was not revision class session. Now I didn't put any sessions on Sunday. But Sunday I will do a past paper. At least now there are 9 essay questions when you consider for the last 35 years of exams. So there were 9 essay questions came. Right, target is at least to discuss 3 essay questions on Sunday. Then tomorrow we'll plan there are around 40 MCQs from Elasticity. We'll try to discuss at least 25-30. Then Sunday, three essay questions. Then next week, we can do tute questions. And sometimes tomorrow, I might do tute questions. Tomorrow, 6 to 7, no, 6 to 7:30, I will do a tute question session. Next, tomorrow, I will inform. Likewise, we are doing tute questions. The next day, we are starting viscosity. Monday, theory class starting. Tuesday, also, I will do a viscosity theory class. Likewise, Saturday, Sunday, I will give the time for the electric field. So that is the way we have to do these classes. Okay, right. Okay. So I am the last topic. The last topic. The last topic. Write down. Give me 1 second. Right. Hmm. Give me 1 second. Okay. So write down expression for stress build-up. Expression for stress build-up. Expression for stress build-up due to change in temperature of. Due to change in temperature of. Due to change in temperature of clamped rods and strings. Clamped rods and strings. Clamped rods and strings. Clamp rods and strings. So this is the last story. This story is really, for some students, it's really very confusing. Right? I explain the theory now. Sometimes I will give the note in next day. No, up to now the theories are very simple. Only this graph part is there, but I took time to explain the graph story also. I think up to now everything is very clear. The last theory section, that is also not difficult, but some students they sometimes they don't understand the last theory section. Okay, right. Now there's a rod. That rod is clamped at their both ends. If not, you can say that there's a rod which is under its natural length. That rod is trapped in between two fixed walls. You can tell the rod that natural length is clamped at both ends. So that natural length rod is trapped in between two vertical walls. So both are the same idea, right? Both are the same idea. This is the rod. So nice listen. Let's say now there are two vertical walls. These vertical walls are fixed and has a very good strength than the rods. Initially, rod is at the natural length. Then let's say initially temperature the rod is the room temperature theta something. Natural length of the rod is simple, and the rod is at a temperature theta 1, maybe room temperature. So then we know that if the rod is at its natural length, rod hasn't undergone deformation. That means there isn't any elastic force developed on the rod. There isn't any external forces applied on the rod. That story is clear. So also I take the identical rod, same rod. If I take it out, just think there are two identical rods. There are two identical rods, right? Made same material, same cross section area, same length, identical rod. That identical rod is also at the room temperature. What is the difference between these two rods? This rod is trapped in between two vertical walls, but this rod is free to move. In the event of extension, this rod is free to extend. That is the only difference between them. That is the only difference between them. Okay? Right. Okay. Same rod. Now you want to compare what will happen for this scenario and this scenario. Then only you will understand. Same cross-sectional area, identical. Identical. So now what you are doing now, now you are going to increase the temperature of the rod. Initially, it is at the room temperature, theta 1. You are going to increase the temperature by, let's say, delta theta amount. You are increasing the temperature by delta theta amount. So now what would happen for the rod? If the rod is trapped in between, generally we know that, generally in unit for heat you learned under solid expansion, linear expansion, we learned that when there's a rod of natural length simple L, when the temperature is increased by delta theta amount, we learned that that rod undergoes expansion. The length of the rod will increase by delta L amount, right? Delta L means L alpha delta theta. For this rod, that is true. The rod is at theta 1 temperature. When the temperature of the rod increases by delta theta amount, then we notice that this rod undergoes expansion. This rod undergoes expansion. Now length of the rod means simple L plus that expansion L plus delta L. Now length means simple L plus delta L in info heat. This is a normal unit for linear expansion story. If you want to find this increased length for expansion of the rod, you know the equation, you remember delta L means initial length is L, linear expansivity of the rod is alpha, change in temperature delta theta. Initial temperature is theta 1, final temperature is theta 2 something. So then we know that delta theta means theta 2 large temperature minus smaller temperature is theta 1. Delta theta means theta 2 minus theta 1. That's true. So you guys know. This story is clear. This story is clear. This story is very clear. Usual story. It's a usual story. The problem. The problem is, this is the problem now. When the rod is free to expand, when you increase the temperature by delta theta amount, obviously rod undergoes expansion. Its expansion delta L. This story. What will happen if the same identical rod, the same rod is trapped in between two vertically fixed walls? If not, the both ends are clamped such a way not to expand. If you clamp both the ends, sometimes when you clamp both the ends can't move, both ends can't expand. In that scenario, what will happen? Same rod, naturally simple, initial temperature theta 1. Now you are increasing delta theta temperature. Now you are increasing the temperature by delta theta. Then what will happen? Obviously, now this rod actually, the rod's mindset is the rod wants to expand. When the temperature increases by delta theta amount, actually rod wants to expand. Please let me expand. Please let me expand. Allow me to expand. Why? Because my temperature is increasing by delta theta amount. Please allow me to expand. But the two bodyguards, the two vertical walls, are they allowing the rod to expand? No. So they are not allowing. Now you want to leave, so you are pushing both the bodyguards and you want to leave, but they don't let you to leave. But you are pushing. Actually, rod want to expand, but these two vertical walls don't allow the rod to expand. But rod wants, please let me leave, let me leave, let me expand, Rod wants to expand. As a result, rod can't expand. As a result, what will happen? Rod is creating kind of stress. Rod is creating kind of forces. Rod is creating kind of stress on both the walls. Rod is creating as a result. If the rod is telling, if you can't let me expand, then I apply stress on both of you. I apply stress on both of you. As a result, we know that there will be a stress developed on both the walls. There will be stress developed on both the walls. There will be stress developed on both the walls. Right. So rod applies stress on both the walls. Right. So what is this? You can tell that the stress, the force produced by the, now the area is capital A, area is capital A. What is if the force produced by the rod on the wall? The force produced by the rod on the wall by the rod. If you divide by the area, that is the stress produced by the rod on the wall. We know that every action has equal opposite reaction. So when the rod applies force on both the walls also produce equal and opposite force on the rod. 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 If this story is very clear. Actually, there's a rod initially in the simple lil. When the temperature of the rod increases by delta theta amount, rod wants to expand, but both the vertical walls are not allowing the expansion of rod. As a result, rather than expanding, there will be a stress. There will be a stress. There will be a force developed on the rod. There will be a force. There will be a stress force. So there will be a stress developed on the rod. What's our target? Our target is to find the stress developed on the rod, though the external force developed on the rod. That's our target. Our target is to find if. Our target is to find if. Now, so what is the link between this story and this story? The link between story and story. So they are telling, right? This force is exactly same to the force that you apply on a rod of length L plus delta L to compress to a length simple L. They are telling, right, when you increase, when there is a rod trapped in between two vertical walls, when there is a rod at natural length which is clamped at both the ends, when the temperature is increased by the theta amount, the developed force on the rod, the developed force on the rod is exactly equal to the force required for a rod of length L plus delta L to compress to a length L. Length L. That is the idea. That is the idea. That is the idea. Raise your hands. That story is crystal clear and some. That story is very clear and some. That story is very clear and some. Very clearly. So then, so you can think that, you can assume that there is a rod of length L plus delta L. So when you apply a force, it undergoes a compression L. So this is something related to elasticity. Compression. There's a reduction in length when you apply a force. Then you can apply the equation. That equation F over A Young's modulus E over L. If not elastic modulus E over L. Right. So you want to find capital F applied force. You want to find capital F applied force that is equal to the force developed on this rod. Cross-sectional area remains same, but actually it's changing. But we are assuming cross-sectional area remains same. That is capital A. Young's modulus is Y. Change in length. Initial length is L plus delta L. It is decreases to simple L. The change in length will be what? L plus delta L minus L over initial length is L plus delta L. Initial length is L plus delta L. So we are writing F over A equals, this will cancel out, Y delta L over L plus delta L. Correct me? So what we are doing, we are telling that when you compare with the L, delta L value is very small when you compare with the L value. For example, L is 5 meter, delta L is some kind of 1 centimeter, 2 centimeter. When you compare with simple L, delta L is very negligible. You can say that you are coming with a conclusion. You are coming with an assumption. You are telling that. So L plus delta L, we can approximate to L. We can approximate to L. We can approximate L. So therefore, we can write down F over A means Young's modulus delta L over L. Delta L over L. Okay. Now delta L means we know that in expansion heat, unit for heat, we learned that delta L as L alpha delta theta over L. F over A. Finally, you can cancel out L and L. You can write down F equals nothing but move this A that side. F equals AY alpha delta theta. So this is this. If they ask you if they ask you in a question, when there is a rod of natural and simple nil clamped at their both ends, and when the temperature increases by delta theta amount, what is the developed stress? What is the developed force on the rod? Means you will tell that that is equal to A Young's modulus alpha delta theta. Must learn by heart. Must learn by the story. Okay. Genuinely hands up. This idea is very clear answer. This idea is very clear answer. This idea. So better write on the story, but I will give the theory note next day. Theory wise, that's it. Theory wise, that's it. When I do questions, stupid questions, I will tell you some patterns and when the cross sectional area and when the length, some stories are there. So I will tell you those stories when I do stupid questions. Tomorrow I will do past paper MCQ story. Sunday I will do past paper essay story. Then tomorrow night 10 p.m. to 12:30 only past paper MCQ story. Tomorrow, if I come a bit earlier, I will do 6:30 to 7:30 something. I will do 1 hour session for tutor question discussion. Likewise, I am doing. So whenever I get time, I put classes. If you can't come, then watch the recording. Better you I can't. It's up to you. Generally, hands up. This stories today's stories. Everything is crystal clear. Hands up. Everything that we discussed today, everything is very clear. Hands up. All the points are very clear. Very clear. So right. Okay. So then class session is effective also. Hands up. It's effective. Session is effective. Right. Okay. Then okay. No issues. And yeah, so then we'll stop the class for today. And these days we are having